Hello, and welcome to a discussion of electrons and their potential energy. This will be the first portion of our discussion of the lesson of voltage, current, and Ohm's law. Now, to be able to understand the behavior of electrons in a circuit, we need to understand a little bit about the forces that control that behavior. And in particular, figures 1 and 2 in this lesson really illustrate the most important principles behind the behavior of electrons and their forces. You can see in figure 1, two charges that have the same polarity are going to be repelled from each other. So two electrons will be repelled from each other, or two protons will be repelled from each other. But as you can see in figure 2, if there are two charges with opposite polarity, one positive, one negative, they'll tend to be attracted to each other. Why is this the case? We don't know. It's a fundamental law of physics, and all we can do is build a world upon which we take advantage of this fact. Now, there's another fact that's good for you to know, and that is that the electrons are probably more important to us than the protons. The electrons are free to move around the circuit, whereas the protons are bound to the nucleus of the atoms. And the atoms, of course, are held in a matrix and they're not allowed to move. So it's only the electrons that will be moving. So if we focus on the behavior of electrons, as you can see in figure 1, electrons will be repelled by other electrons, and electrons, as in figure 2, will be attracted to protons. And that's very important for us to understand. They will be repelled by other electrons, and they'll be attracted by protons. So moving electrons closer to other electrons will require us to do work and add potential energy to the system. And similarly, if there are electrons that are in the midst of protons, it would take work to pull it away from those protons. How do we do that work? Well, we apply external forces. We apply battery power. We plug the circuit into the wall. If we didn't have any external sort of electromotive force in the system, then the electrons would move to a position where they were satisfied, and then they would never move again. Of course, that's what happens when we unplug something or when we take the battery out of it. Now, a second way to think about this behavior is to think of it in terms of the electron's potential energy. You can see here a system in which there's a huge cluster of electrons on the left-hand side and a large cluster of protons on the right-hand side. You might ask yourself, where would the electron prefer to be? Well, it would definitely not prefer to be at point A. Point A is at a very undesirable location, surrounded by all of these repellent electrons. But point B is very attractive. It's surrounded by all of these attractive protons. So we can represent that mathematically by the potential energy. And you can see the potential energy is very high at a place where we would have to do work to put the electron into that location. And the potential energy is very low at a place where we would be able to just let the electron go there and achieve its lowest potential energy. You know, like a couch potato, the electron will go to the point of lowest potential energy and it will just stay there until we disturb it. And so this is a second way of thinking about the behavior of the electron. We can think about it first as being repelled by electrons and attracted by protons, or second, we can think of it as going to the place of lowest potential energy. Imagine if I put an electron here at a point of very high potential energy at point A, it would naturally flow down to a point B, which is at lower potential energy. Very important to remember because that's going to ultimately be the foundation of Ohm's law, that a voltage difference will lead to current flow. Well, I use that word voltage probably a little bit prematurely here because so far we've only talked about potential energy. It turns out that the potential energy depends on the size of the charge that we're moving to that location. In the same way that if I said to you, hey, will you please pick this rock up over your head? Well, your first question should be, how heavy is that rock? Because if it's a little pebble, that's no problem. But if it's a boulder, that's going to be a lot more work to pick up that rock. So we want to normalize. We want to divide by the charge to make sure that we're talking about potential energy per unit charge. And when we do that, we get a quantity that's known as voltage. So you can see here that the equation 1, which is going to be the potential energy, U, divided by the electric charge, Q, will give us the voltage, V. Voltage is one of the two most important quantities to an electrical and computer engineer. We don't tend to talk about potential energy. I know that you're accustomed and comfortable with potential energy from your extensive physics studies, but as electrical circuit analysts, we will be studying voltage, potential energy per unit charge. So this voltage is going to be very valuable to us because we can do a lot of things with voltage. Now, there's two last things I want to tell you about voltage before we wrap up for today, before this lesson, is that, first of all, if you're going to measure a potential energy at any point in the circuit, it needs to be relative to a reference point. In the same way that if we wanted to know what is the elevation of Valparaiso, we have to have relative to a reference point. Now, elevations are taken relative to sea level. That's the reference point for elevation. But if I were to report that Valparaiso has an elevation of 794 feet, it is implicit that that is relative to sea level. In the same way that if I said, hey, what's the elevation of Denver? Well, that's 5,280 feet relative to sea level. We usually skip that relative to sea level part, but if there's no reference point, then you cannot specify an absolute voltage or an absolute elevation at any point in a circuit or at any point on the Earth. Notice, though, that you don't need to select a reference point if we're talking about the voltage difference between 2 points. To say that Denver is 4,486 feet higher than Valparaiso, I don't need to say whether that's relative to sea level or relative to the top of Mount Everest or relative to the center of the Earth. I just need to know that Denver is 4,486 feet higher than Valpo, and therefore the difference between 2 points, we're not going to require information about a reference point. So now you're ready to solve the energy and voltage example problem. I'd encourage you to try it on your own and then watch the video that talks about the solution. Then come back and we'll talk about current and the motion of charges. Thank you for your attention.